Welcome to our study of the fundamentals of operating systems, based on the textbook Operating Systems Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter B. Galvin, published by Wiley Publishing. Glad to have you back. We have just finished Module 2 on process management, which covers the requirements and alternative solutions for managing the scheduling of the CPU for active jobs in the system. Now in Module 3, we get to dig deeper into issues that must be addressed when those processes interact with one another, sharing data and code. We've already talked at length about processes that cooperate in some manner with other processes. And we have already discovered that these cooperating processes not only communicate, but while doing so can interfere with each other and possibly cause errors in the common data when accessing that data at the same time. In another unit, we learned that the processes can either directly share a logical address space, referring to both code and data, or be allowed to share data only through shared memory or message passing, as we talked about earlier. However, we must be aware that concurrent access to shared data may result in data inconsistency. Let's say, for example, that we're managing a database of information about helicopter parts. In our example, let's have one technician, Alfred, who's just changed out a part and is updating the maintenance record to reset the mandatory replacement date for that part. At the same time, another technician, Hasim, is updating the same record to update the vendor ID for that part. Alfred opens the record to record the change in the replacement date. Hasim then opens the record to change the vendor ID. Alfred finishes his update and saves the record. Hasim finishes updating the vendor ID and saves the record. Now, if one looks at that part's record, what do you suppose the mandatory replacement date is now? Did Hasim overwrite Alfred's update? In a modern database, probably not, because the coding of the database application will have prevented it from happening. But what kind of coding might that be? While a database example may not be the best means of illustrating the problem, I imagine you get the point. In a multi-core, multi-processing cooperative world, some resources must be protected from concurrent access by more than one process. In this chapter, we discuss various mechanisms to ensure the orderly execution of cooperating processes that share an address space so that data consistency is maintained. Previously, we found that processes can execute concurrently or in parallel. We learned about the role of process scheduling and described how the CPU scheduler switches rapidly between processes to provide concurrent execution. Concurrent execution means that one process may only partially complete execution before another process is scheduled. In fact, a process may be interrupted at any point, and the CPU may be assigned to another process. We also learned about parallel execution, in which different processes execute simultaneously on separate processors or processor cores. Now let's see how concurrent or parallel execution can contribute to issues involving the integrity of data shared by several processes. Let's consider an example of how this can happen. But let's consider it in the next lesson. This is a good introductory lesson right here. So let's take a break. You go back and take a look at your notes, take care of any business you need to take care of, and we will come back and take a closer look at this problem and how it can be solved.